Okay, so in this video, I'm going to give an intro to how to frame minimizing the initiation interval as an integer linear programming problem. So just a review from last time, we're working with this simple example function that iterates over the entries of a loop, setting the ith, or entries of an array, setting the ith value, or the ith entry of the array to the I minus 2th entry plus 1. And again, just for simplicity, let's suppose that instead of compiling this down to a bunch of little instructions, the architecture that we're compiling to can do this whole statement as one instruction, and that instruction takes 3 cycles, so that a sequential execution of the loop will have an initiation interval of 3, and it'll look like this. We'll do the first iteration of the loop, then the second, then the third. And the first iteration of the loop is going to write to A2, and the third iteration of the loop is going to read from A2. So the store that happens at the end of the first iteration of the loop has to come before the load at the third iteration of the loop. And in our example from last time, that would mean storing the value 4 and then loading the value 4. So with an initiation interval of 2, the store and the load get closer together, but we're still respecting this store-load dependence, even though we're getting faster than sequential execution. And then when we go all the way down to an initiation interval of 1, the load crosses over the store and we violate this data dependence, right? We store the value to A2 after the load, even though in any legal sequential execution, the load would have to be done after the store. And in our example data from last video, that would mean loading the value 2 from A2 instead of the value 4, which is what we should see. So that should make sense intuitively, right? The smallest legal initiation interval is 2 because an initiation interval 1 violates the store load order here, an initiation interval of 2 doesn't. And we want the initiation interval to be as small as possible, so the best initiation interval is 2. So how do we express this to a scheduler that can handle integer linear constraints and that treats scheduling as basically a linear programming problem? So well, to start, let's just phrase the problem in words, right? As I've said before, the loop pipeline schedule, or a pipelined loop schedule, really is just an ordinary schedule for the body plus the initiation interval. And the constraint we have here is that, well, we have all the constraints for the normal loop body schedule, plus the constraint that the first iteration of the loop has to finish before the third iteration starts. And notice that in our ordinary loop body schedule, each iteration is going to take 3 cycles. So actually, this phrase up here can just be translated into an integer linear constraint using our notation for start and end times of instructions, like so. We can say that end underscore 1 of ai equal to ai minus 2 plus 1. In other words, the instance of this instruction in the first iteration of the loop has to end at a time that is less than or equal to the start of the instance of that instruction in the third iteration of the loop. So in other words, the end of this instruction in the first iteration of the loop has to be before or at the same time as the start of that instruction in the third iteration of the loop. And that's just a symbolic representation of the constraint on the order of the store and the load that we saw visually in the pipeline execution diagrams earlier. So how do we simplify this down and express this in terms of the initiation interval and the starts and end times computed for instructions in the ordinary loop body schedule? Well, just remember our instruction completion formulas, right? This is equivalent to the end time of this instruction in the ordinary loop body schedule plus the initiation interval times 1 minus 1 is less than or equal to the start time of that instruction in the ordinary loop body schedule plus the initiation interval times 3 minus 1. So this simplifies down to, well, the end of this instruction has got to be less than or equal to the start of this instruction plus 2 times II, right? Because 1 minus 1 is 0, 3 minus 1 is 2. And actually, since we have a schedule, and we know that because each instance of this instruction takes 3 cycles, the start of the instruction is in cycle 0 in the ordinary loop body schedule, and the end is in cycle or state 3. So we can reduce this down to the constraint 3 is less than or equal to 2 times the initiation interval. And so actually, we can use this constraint to phrase an integer linear programming problem for the initiation interval. We can say that what we need to do to compute the II is we're minimizing II, and this is a linear constraint, or a linear objective function, excuse me. And we can minimize it subject to the constraints 3 is less than or equal to 2 times the initiation interval, and 1 is less than or equal to the initiation interval. So this is just a constraint that will always be there for any initiation interval computation problem, and this is our loop-specific constraint. So let's just try to solve this manually. Well, let's try the smallest possible initiation interval we can get with this constraint, which is 1. Well, if the initiation interval is 1, 1 is less than or equal to 1, so that's fine. But then we'd have 3 is less than or equal to 2 times 1, which is 3 is less than or equal to 2, which is logically equivalent to false, right? So the initiation interval of 1 doesn't work. So let's increment by 1 and try the next smallest initiation interval, 2. Well, now, that should be 1 is less than or equal to 2, excuse me. And we have 3 is less than or equal to 2 times 2, which is logically equivalent to 3 is less than or equal to 4, which is logically equivalent to true. So the smallest possible initiation interval is going to be 2. And indeed, an initiation interval of 2, which is the solution to this integer linear programming problem, is the correct solution to the initiation interval computation of this simple loop. So this is a very simple way, though maybe not necessarily the most compute-efficient way to compute a pipeline schedule, but all of the big algorithms for finding pipeline schedules for loops basically work on this kind of integer programming formulation. Now, we skipped some pretty important steps about how to actually find the constraints on the initiation interval automatically. So for next time, I want to deal with the question of how do we automatically generate constraints for this ILP problem for more complicated loops. What do we do about situations where we can't just list out the dependencies between each iteration of the loop? And what do we do about finding approximations of dependencies that are safe for more complex memory access patterns? So those are all things that we'll explore in subsequent videos, and they're one of the most important parts of any high-level synthesis tool.